Hello, welcome back to the channel. So now let's go over some more properties of definite integrals, and I would say that these are indeed one of the most interesting properties as well that we'll cover in this video. So we'll go over these properties, but if you want to prove these properties, we'll not extensively prove these properties, but I'll give you a hint on how to prove these properties. And if you want to prove these properties from the scratch, you will again use the Riemann sums. And these questions will be totally based on just one notation that we use in order to convert a definite integral into a Riemann sum, which is the sigma notation for I goes from 1 to n fxi delta x. I'll not include the limits in order to not make it more complicated, but the basic idea about proving this thing, proving all these properties, is based on this part right over here. And you can easily prove all those properties by considering this expression and proving these theorems that we'll cover in this video. So now we'll start with the properties. Again, the same thing. We have considered that a, b, c are the constants or the real numbers that we have, and fx is our integrable function. And the first property is, if you're taking an integral of fx where you have the starting point and the ending point the same, your area under the curve would be 0. And that makes sense as well, right? For example, in this case, if you'll take the area under the curve of this infinitesimally thin vertical strip, you'll get the area as 0, right? Because the starting point and the ending point is same, and this can also be calculated by using this expression that we have over here. And you also know that whenever we calculate delta x, our delta x is always b minus a over n, right? And in my case, when both my starting and ending values are the same, so my b would also be equal to a. And if I calculate this expression when my b is equal to a, it would become a minus a over n, and that would be 0. So your this expression, your sigma expression, would become 0, and that is why you have this expression as 0. So that is why all the theorems over here are completely based on this expression. And if you know how to evaluate this expression and simplify it down, you'll prove all these three expressions. So now let's cover the second property, and the second property says that whenever you are calculating this expression, the area under the curve for a function, starting from b to a, this would be the negation of taking the area under the curve for the same function, but reversing the endpoints. And if you want to prove it, you'll again use this expression to prove it. You'll see that whenever we take xi, we are considering all the y points over here, right? So we know that the y points will not change. If I start from here and add all my y points, or if I start from here and add all my y points, this expression would be the same, right? My sum of fxi's would be the same, because it doesn't matter if I start from the left hand side or the right hand side in order to calculate the sum of my y values. But what matters is, in this case, is delta x. And you know that since delta x is b minus a over n, when you're taking the definite integral from x equals a to x equals b, it's b minus a over n. But if I reverse my endpoints, my delta x would also be reversed, right? Because now my new delta x, if I denote it with delta x star, that would become a minus b over n, because in this expression my b is a and a is b. And now based on both of these delta x expressions, you'll clearly notice that this delta x is the negation of this delta x over here. And that is why you have this property over here, which can be also easily proved. So now let's move on to the third property. The third property is very easy to prove as well. If you evaluate this expression, you'll clearly notice that this property holds true, which is about breaking your definite integral into multiple parts. So if you have in this case your a is less than equal to c is less than equal to b, you can always split up your interval like this and calculate the individual portions separately and sum them up. So that is a third property, and we can clearly visualize it as well, right? If I have this c over here, which is dividing my interval into two portions, if I am taking the area under the curve from a to b, that is basically the same as taking the area under the curve for a to c and taking the area under the curve for c to b and adding both of them together. And that is what we did on the right hand side, as you can clearly see. So now these are the three properties that are one of the most interesting and also one of the most useful properties as well in definite integrals. So now based on these properties, let's do a simple example in order to reinforce this concept about the arithmetic for the domain of integration. So let's simplify this expression and evaluate this expression over here. So you're given that your integral of cos x dx starting from x equals 0 to x equals b is sine b, and based on this information you have to calculate this expression over here, right? So now let's use all those three properties above that we discussed in order to solve this question. So I can write my integral a to b cos x dx as, so if I see this expression, it gives me an idea that I have to somehow bring a 0 in one of the endpoint cases. So why not use the third property and divide our definite integral into two parts such that we have 0 between a and b in this case. So if we do that, we can write this as integral a to 0 for cos x dx plus integral 0 to b for cos x dx by using the third property over here, that is splitting our definite integral up. And now the only thing that is left is to convert this definite integral somehow that we have a 0 for the left endpoint such that we have a similar looking expression of this one. And we can clearly use the second property over here, that is swapping our endpoints. So we know that if we take the integral of 0 to a in this case, we'll have to negate this definite integral, right? So it would become negative of integral 0 to a cos x dx plus 0 to b cos x dx. And this expression we know over here based on this formula that it would be sine a in this case, and the next portion, the second portion, would be sine b in this case. So now my final answer becomes sine b minus sine a, which is equal to integral a to b cos x dx. And that is the final answer that you have over here. So you noticed how easy it was to evaluate this integral based on the properties that we discussed, and in most cases as well, these three properties indeed make your calculations for definite integrals much easier. So that's it for this video. Feel free to comment down in this video if you have any doubts. Please follow the channel in order to get notified about the other videos that I'll be uploading. Stay tuned. Thank you so much for watching. Bye bye.